Today, we are talking about a really special type of supersonic airfoil, and that is the double wedge one. As you can see in these figures, the double wedge airfoil is effectively a diamond-shaped one and is one of the most commonly used ones in supersonic flow. The other very common type is a biconvex airfoil, which is very similar to a double wedge airfoil, but the upper and lower surfaces are curved instead of very angular as we see here. And I don't know about you, but for me, the double wedge airfoil always struck me as a little odd because most airfoils are very sleek. This one isn't. But it's also true that these sleek airfoils are usually for subsonic flows, and these double wedge airfoils are for supersonic flows. And today we are talking about how supersonic flow behaves over a double wedge airfoil. To do that, we are looking at this paper called, if I scroll up, Evaluating Oblique Shockwave Characteristics on a Double Wedge Airfoil. And this is open access, so you can find it in a link below. So there are a couple cool things about this paper. I mean, not only does it consider double wedge airfoils, but it also does CFD and experiments. So let's first talk about their experimental setup. So they have their supersonic wind tunnel as shown in figures 1 and 2. And their wind tunnel features a converging-diverging nozzle at the start to boost the velocity of the fluid, as you can see here in figure 1. For those of you who don't know, this is actually a really cool feature of supersonic flows. So in subsonic flows, if you have a converging-diverging nozzle, when the fluid enters, it accelerates as the cross-section reduces, that area, and as the cross-sectional area increases, again, the velocity drops accordingly. That's just from Bernoulli's equation and mass flow rates, and continuity of momentum, etc. But strangely, when you get to around transonic speeds, something weird happens when you have a converging-diverging nozzle. So let's say the flow entering is subsonic to begin with, and then when it reaches the point where the cross-sectional area is lowest, it is now sonic. Now, when you diverge the nozzle, so the cross-sectional area gets bigger, the velocity will actually increase as well, instead of decreasing, which is what would happen if you had the flow as subsonic in the throat section. So, this allows you to create a supersonic flow from a subsonic flow through this converging-diverging setup. And that is what they are doing here with this wind tunnel. Then the flow hitting the test section is supersonic. So the velocity they used here was Mach 1.6, and the measurement technique they used was Schlieren, which we kind of covered quickly a couple podcasts ago, but I want to cover a bit more here. So Schlieren is probably the most common supersonic wind tunnel technique, partly because it gives quite useful information, and partly because it is very easy to do. And let's go through a bit more in detail what this is here. So the general operating principle is that when a fluid's speed suddenly changes, like over a shock, the refractive index of the fluid now changes, so how much it bends light. So in the case of a shock wave, before the shock, the fluid will be refracting light a certain amount, which in layman's terms means it's bending at a certain amount. Then directly after the shock, the fluid, which is at now a much lower velocity, will refract the light a different amount. That results in a discontinuous image, and the shocks appear as very clear lines as shown in figure 3. So if I scroll down here, these lines here, they're these black parts. So in its purest form, Schlieren uses a collimated light source, which is one where all the light rays are parallel to each other. However, in modern times, we use a slightly different setup, which is essential. It's essentially just like you point a light source in the flow, then once the light has passed through the test section, it hits a mirror, and then it redirects it and focuses it on the edge of a knife blade. The camera is now placed behind the knife blade because different flow velocities refract the light a different amount. Some of the light will then not pass over the knife edge into the camera because it no longer is hitting the mirror right. This then results in the image that you're taking featuring light and dark regions. The light regions are where the light did make it past the knife edge and into the camera, while the dark regions are where it didn't. Hence, you can visualize the shock and in the supersonic flow, so as long as there are shock waves, that is. If there aren't any shock waves, then you would just see a lot of light. Now, that is the operating principle of how Schlieren works, and both the old and the new methods that we use. These researchers are using Schlieren here to give our eyeballs some interesting things to feast on. In addition to that, they also used CFD, and from what I can tell, they used the RANS model with a K-epsilon terminus model. Now, they say in a previous study that the Spallert-Almaras terminus model was used, and that piqued my curiosity because originally, the Spallert-Almaras terminus model wasn't intended for use on highly compressible flows. In fact, it wasn't really intended to be used on even slightly compressible flows either. It was really just meant for low speeds. And these researchers used it for supersonic flows previously. So I looked up how well the Spallert-Almaras model worked for compressible flows. And it turns out that the original model, unsurprisingly, is terrible at it. But if you modify it, it can actually predict compressible flow physics quite well. The typical way to modify it is to account for the local density changes when you're calculating the viscosity. Hence, you take into account the changes in the density. And there is actually a paper out there called Review of the Spalled-Almaras Terminus Model and its Modifications of Three-Dimensional Supersonic Configurations by a guy, Sedemir Kostic. I don't know if I pronounced that right, for those interested. So I'm not sure why the authors went with the K-epsilon model here. Perhaps the Spalled-Almaras model they had to begin with wasn't that good. But anyway, in figure 4, we see the CFD setup. So let me go down to that. Here we go. And one thing that strikes me is that the inlet is about as far away from the object as the outlet. I mean, usually the outlet should be much farther away than the inlet, especially in a supersonic condition where there are no upstream effects. So I don't know why the inlet is so far upstream. The authors didn't seem to do a mesh-independent study either, which isn't good. But they do have the validation data shown in figure 9. So let's jump down to that figure, all the way down here. Okay, here we go. So let me zoom in a little bit actually as well. Okay, so in figure 9, we have 2 lines in the graph showing the Mach number along the double wedge for the CFD and experiments. I don't know which line corresponds to the CFD and which corresponds to the experiments. So I think this graph wasn't really that well made because there's no legend here. Another reason why I say that is because if you look at the graph, how they have it, apparently the Mach number over the airfoil was also 1.5, which isn't obviously the case because if you look at other figures, for example, if you go to figure 5, if I scroll up here, in figure 5, we see the Mach number color plot, and the Mach number changes quite a lot over the airfoil and shocks form. So in fact, over the front part of the airfoil, the Mach number drops to about 1.3, and then it increases over 1.7 past the airfoil. So this aligns much better with the back portion of the plot of this graph. So we see in this graph that these Mach numbers do change pretty much how we see it in that figure. So I'm pretty sure that this figure is not aligned properly with this double wedge airfoil. So we can conclude that this airfoil diagram here doesn't actually align with the actual airfoil, but rather where we see the maximum and minimum in the Mach number, this is more around where the airfoil starts, and that this is like the minimum is more around like the first half of the airfoil, the maximum is around the second half of the airfoil. Knowing that, let's analyze this graph now. So before the flow hits the airfoil, the CFD experiments give the exact same Mach numbers, and that is to be expected because this flow is supersonic, so even if you have inaccuracies downstream, that information can't propagate upstream, so it's not going to affect what you have upstream. Now, as the flow hits the airfoil, the CFD and experiments follow each other quite closely, but not perfectly, but pretty close. They both show that over the front portion of the airfoil, the velocity drops, and that makes sense because this airfoil is creating a shockwave ahead of it, and that results in the velocity dropping after it. Now, they give pretty similar minimum Mach numbers, both around 1.36, 1.37. As the flow progresses over the rest of the airfoil, both the CFD and experiments give very similar results again, where the Mach number increases substantially, this time up to around a Mach number of about 1.6-ish. Up until here, the CFD is doing a pretty good job in matching the experiments, but then behind the airfoil, this is where the CFD starts to become a little inaccurate, and this is to do with the wake of the airfoil, so this region around here. We see that the CFD predicts another drop in the Mach number, and the reason I now know that this is the CFD, this line that sees the drop here, is because in figure 5, which gives the CFD Mach number color plot, it shows a fairly low Mach number in the wake here, and then it goes quite low and then jumps back up a little bit. So in other words, the CFD is predicting a more severe wake compared to the experimental results. So from this validation section, I think that the CFD is definitely good up until the wake. Then past the wake, it gets the general idea wrong. I guess the general idea right, sorry, but the magnitudes are a bit wrong. But it doesn't predict the recovery very well either. So why that is, I'm not sure. Personally, I would really have liked to see a different terminus model, a comparison perhaps between the K-epsilon and the Spalled-Almaras that they originally had, or look at a different terminus model to see if that was the thing causing these inaccuracies. Alternatively, maybe it was something to do with the mesh. Again, there was no mesh independent study, so it could very well be that the wake maybe wasn't refined enough, or maybe over the rest of the airfoil. So it really seems that some of these things may be the case, we just don't know. maybe weren't meant to know. So taking all that into account, I'm going to rate this CFD around a 7 out of 10. The trends are good and much of the Mach numbers are very good. It's just the wake region is a little bit off. And it's actually quite funny because the supersonic nature of the CFD made their CFD more accurate because any inaccuracies downstream of the inner CFD didn't affect the upstream part. So the upstream part was insulated, hence how the supersonicness of the setup actually helped them here. Usually it's like people go, oh, supersonics are really hard, but here it's actually helping them. And talking of CFD, if you want to learn how to do OpenFOAM, which is a very powerful CFD software and free, but really hard to learn, take our course in the link below. But now let's move on to their CFD results because there are quite a few interesting points to talk about. So going back to figure 5, we have the Mach number across the airfoil, this one here. I'll zoom in a little bit as well. Okay, wunderbar. Okay, so the free stream flow is around Mach 1.5, this yellow region here. To begin with, we have a typical oblique shockwave, and this oblique shockwave forms because you have such a fast moving flow, and then you have this object in the way. And the reason why shocks form is because the flow cannot move out of the way fast enough. Air, and any fluid for that matter, can only move so fast. And if you try to push it out of the way any faster than that, it can't do it. As a result, you have all these air molecules cramming together, and that forms this like barrier, and that is the shockwave. And depending on the Mach number and the shape of the object trying to push through the shockwave will occur at a particular angle. Here, the angle is 47 degrees to the horizontal. And as you travel faster, the angle gets more and more acute. And to give you a quite easy to understand reason as to why the angle gets sharper and sharper as you increase your speed is when you travel faster, you're essentially beating the high pressure that you've just created. And the faster you go, the more you beat it. So the high pressure you just created is now farther behind you because of how fast you are traveling. That results in a sharper angle. So back to figure 5, we see this initial shock, and then afterwards, the velocity is much slower, this green part here. And the thing about oblique shockwaves is that they are very anisotropic, which means that there is a lot of loss associated with them, and they are not a reversible process. Now, when we get to the back half of the double wedge airfoil, in other words, after the peak, this point here, we now get an expansion fan occurring. And I was actually talking with one of you amigos, Orlando Tillett, about how cool expansion fans are. And I agree, expansion fans are really cool. And let me explain why I think they are cool. So they are shocks to begin with, but they're a series of smaller shocks. And they typically occur in exactly this situation here, in this red region here, which you see, where you have the surface bending down and the flow accelerates over it. And in addition to the fact that you have all these smaller shocks in sequence, the other reason why I think expansion fans are cool is because they are surprisingly isentropic. They are technically a reversible process, and they are not lossy, at least not very much, not nearly as much as oblique shockwaves, for example. So I don't know about you, but to me, that is very unexpected because whenever you learn about shockwaves, it's always about how inefficient they are and not reversible, and they have so much loss and so on and so on. So to find a situation where shocks occur and they are not actually lossy is cool. Now, with this figure, through the expansion fan, the Mach number increases a lot. And in fact, it is the highest here out of anywhere in the flow. Here, the Mach number is over 1.7, which again is a little surprising considering that the free stream velocity is Mach 1.5, and the flow has since gone through an oblique shock, and still the flow accelerates over the free stream velocity. Then, once the flow is past the airfoil, the Mach number drops back down to the free stream Mach number of about 1.5, as well as the wake being present. And we covered earlier how the wake wasn't really predicted all that well. And that kind of makes sense because there were some minor differences in the Mach number along the airfoil. Remember, with the minimum and maximum here compared to the experimental data. And when you get to the wake, well, all the chickens come back to roost and the problem comes to full light. So that was the Mach number. What about the static pressure? So remember that the static pressure is the pressure we can feel. So if you were in the flow, you would feel this pressure here. And I'm pretty happy that they included this because a couple of weeks ago, I was wondering if you could survive a shockwave. And now with this static pressure data, we can get a better picture. So the free stream static pressure seems to be about 18,000 pascals, which is already high. That is 18,000 newtons per square meter, by the way. That's 1,800 kilograms just on you, effectively, because you have about 1 square meter of surface area. After the oblique shockwave, the static pressure jumps up to about 22,500 pascals. And that is interesting because the oblique shockwaves pull so much energy out of the flow in losses, and still some more of the flow's energy that was in the velocity got converted into static pressure. This 22,500 pascals is the highest we are seeing in the flow. And I gotta say, I think this shock would be very survivable even if you literally were right on the airfoil, sitting it and riding it a lot. I mean, when you go diving in the ocean or whatever, going down to 10 meters is the equivalent of one additional atmosphere in pressure, which is about 100,000 pascals, 4 times more than what we are seeing here. So I definitely think you would survive this shock. Now, that doesn't mean that you wouldn't feel it, because if the shock hits you, let's say in the chest, well, that is an additional 22,500 newtons per square meter that you're feeling. And that additional pressure isn't being equalized over your back. So you will have a lot of force pushing you backwards and you'll fall over. And to give you an idea of just how hard that would be to stand up to, the highest velocity I've experienced in a wind tunnel is around 20 meters per second. So I have to walk around. I've walked around a wind tunnel without being strapped in at 20 meters per second. Assuming that I have a drag coefficient of about 1, that still only results in like 240 newtons per square meter on me. At 20 meters per second, I was having trouble keeping my balance and I was routinely being knocked around. Now, I wasn't close to falling down, but I definitely couldn't walk in a straight line. What you would experience here is 22,500 newtons per square meter, which is about 100 times more than what I was experiencing. At that kind of force, you would be thrown backwards. And so I definitely think you would survive this pressure, but you would be thrown around very violently. Anyway, back to the static pressure plot in figure 6. About after the halfway point of the airfoil, now in the expansion fan region, the static pressure drops a lot, by half to about 13,500 pascals. Then in the wake, the static pressure goes back up and almost reaches the free stream static pressure again. But obviously, there is less energy in the flow now, so it can't quite get to the same static pressure anymore. Now in figure 7, we see the temperature across the airfoil. And interestingly, the oblique shockwave heats up the flow by about 15 Kelvin, so we see prior to after blue to that green. Through the expansion fan, the temperature now drops by about 30 Kelvin compared to just after the oblique shockwave, and that kind of makes sense considering that we are now expanding the flow, so naturally the temperature will drop. Then in the wake, expectedly, the temperature rises and almost reaches the free stream temperature, as you can see here. Now finally, let's move on to the density because we see some really cool results. So in figure 8, we see that in the free stream flow, the density of air is about 0.33 kilograms per meter cubed. The oblique shockwave really compresses the flow and the density shoots up to about 0.4 kilograms per meter cubed, about a 30% increase. Then expectedly, over the rear half of the airfoil, where we are expanding the flow now, the density of air drops quite a lot to about 0.25 kilograms per meter cubed, which is about 40% lower than just after the oblique shock. Then in the wake, it gets back up to the free stream values. And that is cool. And with that, we come to the end of our podcast. I really, really liked this one. It had shockwaves and expansion fans. And most of all, I got to figure out if I would survive a shockwave or not. So if you like this podcast, hit the like button and the subscribe or follow button, whichever platform you're on. And if you want to learn how to do OpenFOAM, take our course in the link below, which takes you step by step all the way through how to do OpenFOAM, including even how to install it. We also have other CFD courses there to help you get better. And if you want to make your experiments 2 to 4% more accurate, get yourself an atmosphere hawk. It's an instrument we make. You can find out that in the link below. And if you don't know why you have a 2 to 4% error in your experiments, then we also cover the math in that link as well below. So that is it. And I'll see you in the next podcast. Peace out, amigos.